All right, so can you see the screen?
Yes.
All right. Okay, so let's continue. We were and learning about the methods of transfer of thermal or heat energy, right? And so we started talking about conduction. Conduction is just a method of transferring heat energy. It is done so when the thermal energy is transferred through a medium without any flow in that medium, right? So for example, uh, you have a medium, can be any substance or materials, any metals really. What happens is if I heat this metal, the molecules are going to gain heat energy or thermal energy, and they'll start colliding with their neighboring uh, molecules to transfer heat, right? So in conductions, molecules collide with each other to transfer heat, and that is done when molecules gain heat energy. If so, they can gain heat energy in multiple ways. You can heat, one of the method is to heat the substance, and the molecules will gain that heat energy and start hitting each other. So they'll collide with each other, or you can say with neighboring molecules, and heat will be transferred from one molecule to the other, and then from that to the other, and so on, right? So that's how heat is transferred using conduction. So that means if you were asked what uh, or something like mode of so you can say that conduction is a mode of heat transfer, and a mode of heat transfer that has to do with the collision between molecules, that is conduction, right? So conduction is essentially collisions between molecules. Now note that it is the other important thing is that there should be no flow of the medium, right? So there should be nothing flowing in that medium. So I can write it as no flow of medium. And this point, no flow of medium, will be elaborated when we talk about a convection, which is essentially based on the fact that there is flow, or there is currents going on in convection, which are called convection currents, right? Convection is another mode of heat transfer. And so that's how heat is transferred, and we can say why would an object feel hot if we are talking about a metal, right? So conduction is more common in metals. So is that clear?
Yes, clear.
All right. So even though it's more common in metals, it does not mean that it does not happen in liquids or gases, but the chances, or you can say the probability of conduction is very high in solids, and then liquids, and then very low for gaseous like objects, right? And okay, so that's more or less conduction. Then you have the second mode of heat transfer is called convection. All right. So convection is more or less based on the idea of currents, right? So if you hear the word current, you might only think that it has to do with electricity, but it's not that. That's not the case. Currents are usually anything. If it starts flowing, then then you call it a current, right? So it means that, for example, you're more familiar with electricity. When I say current, it's just when charges are moving or flowing. So for example, if I connect a wire into uh, a plug in the home, if I connect any plug in the switchboard, you can power up your computer or TVs and or other objects, right? And they get powered up because when I connect that, the electrons start flowing in the wire, and the current is basically produced, or the output, you get some current, right? And that current is just that the charges start flowing in that wire. Now, convection is also a method of transferring heat energy, and it's done by something that is called convection currents. Okay, so we can understand convection better by the idea of convection currents, and the idea of convection currents is coming from the fact that there is some change in density of the medium, right? So convection currents entirely depends, or it is defined as the change in density of a medium. Now, why does that make sense? It makes sense because suppose I have a wire. So I'm going to try to draw a circular wire, and it contains charges, right? So let me use another color. So there are charges sitting in this wire. All of these charges are Q. Right? Now, if the wire is not connected to a switchboard, these charges will sit still and do nothing. But as soon as I connect the wire to some plug or a switchboard, the charges will start moving, right? All these charges start flowing. Now, when these charges will start moving, what is happening in terms of density is that it's changing. The density of charges in the wire is continuously changing, right? Because at some point this charge may be here, now it's over here, right? And so the charges are moving. So continuously I can pick any region of this wire. Let me use a highlighter for that. So suppose I pick this region, and the charges, because they're moving in this region, the density is continuously changing. And that change in density of the charges is what we call current. And exactly in the same way, we define convection currents by saying that the density of the medium through which this convection or the heat transfer is going to happen is changing. Right? So now, how can we understand this by using the idea of convection current? Suppose that you have a container and it's filled with water, and I start heating this glass container, which is filled with water. Now, what happens as I heat this container of water? you'll see that water was there. You'll see some vapors or steam rising, right? So that's the steam. Let me draw it in some other color. And it is happening because when I heat the water at the bottom, it's going to start heating more compared to the top. So what's happening is that the water is expanding, and we know that the when water expands, its density is less, right, than the water that has not expanded, for example. So if the water expands, its density decreases. And so you can see where this change in density of the medium is coming in, right? So water is going to expand, its density is going to change, and that's how the it will start rising, because now it's less dense. So eventually it will become can you hear me? Hello?
Yes, I can hear you.
Yeah. So eventually this the less dense water will start rising because it has lost its density compared to the other water, and it starts rising. And this rising water is what we call is what you can say it's the convection current, right? So it's in in other words, you can also define it as the uh, bulk movement of molecules from one region to another, right? Because that's what's happening when the water starts rising. The less dense water, the one that has expanded, is going to rise all together, as in it's moving from one region to another region. And that's uh, actually that's part of the convection, right? Now, uh, before I proceed further into convection, is this idea of changing in density clear?
Yes,
And
clear.
why does it mean that there will be currents, convectional currents, due to that change in density?
Yes, because the particles of the water move because they have more energy.
Exactly, right? Exactly. So it will expand, become less dense, and then less dense water will start rising upwards, right? And that's when the less dense water rises upwards, it means that the cold water will start to sink, right? And this thing to altogether is convectional currents, right? Now, convection is actually a combination of conduction as well, right? So it's so actually writing it like this, uh, I mean, what will I say? It's conduction and convection. That's just a weird wordplay. You can say that the word convection comes from the fact that this part of convection means conduction. So the con stands really for conduction, and this part, it is advection. And advection is what we describe by using the density model, right? So the bulk movement of molecules from one region of space to another region of space is advection, right? Bulk as in a lot of molecules all together, moving all together, bulk motion of molecules. Right. So now, if I say that it happens in liquids and gases, but not solid, would it make sense to you now that why would it not happen in solid? Thinking in terms
Yes.
of uh, what how we describe the changing density.
Yes, I have an explanation.
Yeah,
Solids
go ahead.
cannot flow. Solid cannot flow.
Right, exactly. So solids cannot flow. There is no uh, flowing happening in solids because molecules cannot move in a solid, right? They, if it depends how you describe move, they are surely vibrating in a solid. So you can say they're slightly moving, but they cannot change their position from one point to another point, right? So for example, if this was a solid, I cannot say that this molecule will go over here after some time and this molecule will go over here sometime. That's not going to happen. They will be vibrating, sitting in their positions, but they'll not move. As in, so it's exactly how you described. There is no flow in solids, and this is why there is no flow, which would mean that convection will not happen in solids, right? And using the same thing, you can explain why it would happen in liquids and gases, why it should happen in liquids and gases, because molecules are allowed to move in liquids and gases. So it makes sense?
Yes, it makes sense.
All right. So okay, so that's more or less that's convection. We can talk about the final method of transferring heat, and that's radiation. Right.
Uh,
So
Sir,
yeah,
is there two types of radiation? Infrared and non-infrared?
yes, yes.
Okay.
You can say basically in radiation can be absorbed or it can be emitted.
Okay.
Now, yeah. So what do we mean by that? Okay, so I don't know if you're familiar with this thing. Light is made up of particles, and those particles are called photons. Does anyone have any idea about that?
I think I heard about it once or twice in a video.
Okay, but so okay, so just for the sake of, we can see, so for example, you turn on the light, the room lights up, you can see things, right? Now, why is that happening? Basically, okay, so now when I say particles, you might think of small, tiny ball-like particles, but that's not really how particles are defined. But for the purposes of understanding, you can take it to be as small ball-like objects. So for example, if I have a source of light over here, and you can see that this it throws light, so it's maybe it's a torch or something. So you can say that these beams are really made up of particles. These are a stream, a jet stream of particles flowing outwards. And these particles are photons, right? As we know, I'm sure you have heard about what is an electron and these kind of particles. So photons are also particles. These are particles of light. And when these photons interact with a human eye, that's how we are able to see things, right?
Yes.
Now, when I say it interacts with human eye, the photon is absorbed in the human eye, and that's how you're able to see things. So a photon, for example, let me give you an example. So suppose you're sitting in your room, and you see something. Suppose there is a door over here, and the room is lit up. There's a light everywhere in the room, so you can see the door. Now, why you can see the door? Because wherever the light is, it's just photons which hit this door, and they're reflected back to your eye. The photons scatter at the surface of the door, and they come to your eye. Now, there's not just one photon. There's so many photons. So that's why you can see the entire room, in fact, right? Because these photons are being absorbed as they hit the surface of the door. Whatever part of the door they'll hit, that's what you'll see.
Yes.
Now, why am I telling you this? Is yeah, any question?
No questions.
Okay, so this is how radiation works, or in fact, radiation is just photons, right? So that's the reason that I'm talking about this thing. And to understand absorption and emission of radiation is just to understand absorption and emission of photons, right? Now, there might be a question in your head, at least there should be, that when you turn on the light, then because the room entirely lights up, there should be millions and billions of photons, right?
Yes.
And all those millions and billions of photons are interacting with so many things. So how can we still see things as they are? The things should, if there are so many photons, they should interact with each other as well, and things should scatter, right? So we should not be able to see things.
They are constantly a lot of protons, but the how we can see them is the entering the photons are entering our eyes.
Yes. So for example, there's so many of them, right? There's so many of them. So for example, there's not just one photon. There is there's so many. So when these photons hit the door, what is the probability that they'll not interact with themselves, but only come to your eye? It's very less. Like if there are so many particles, they will eventually interact with themselves, and they'll not clearly reach your eye properly. But if something can only interact if it has a charge, right?
Yes.
If there are charges, actually, these are things that might fly over some of your heads right now, because we still haven't talked about electricity, which is the next thing that we'll talk about. But they're not charged, and charge defines if something will electrically interact, right? And these photons are not charged, and that's why they'll not interact with each other. They'll be just emitted and then absorbed, emitted from a light source and absorbed into, for example, a human eye. And that's how we are able to see.
Yes, they don't have positive or negative charge.
They don't have a positive or a negative charge. They're electrically neutral, right? And same is the case for neutrons. And so there are so many neutrons constantly hitting us, but they're not charged. That's why we don't feel those neutrons. All right. So that was just to give you an understanding of what radiation is. I hope we have enough time so that we can finish off radiation. We have 5 minutes, right? So that's good. Okay. So radiation, radiation is basically photons, right? Radiation is basically photons. In fact, it is entirely photons. And photons is what? It's light. If there are photons, it means there's light. So keeping this in mind, can you tell me, will radiation require a medium? As in conduction requires a medium, convection required a medium where the density changes. What about radiation?
Yes, is it the sun?
Okay, but for example, a medium is defined as what? For example, air, or what I'm trying to ask is, will for radiation to travel across space, does it need any medium? For example,
No,
sound
no,
needs a medium.
no. It does not need a medium.
It does not, right? And that's because, for example, there is a very big sun in our space, and we can see the sun. We can see the sun, but we cannot hear the sun. We cannot hear the sun because there is no medium between the earth and the sun. It's almost empty space, vacuum. That's why the sound never comes to our ears from the sun, because sound needs a medium to travel, either air or a glass or any material. However, light, which is radiation, does not need any medium to travel, right? So that means that radiation can travel in vacuum, right? This statement also tells you that it does not need any material or a medium to travel, right? Okay, so now if suppose we'll discuss now emission and absorption of radiation. Let's do that with an example of, suppose if I have a surface and it's completely smooth, right? This surface is entirely smooth. There are no rough edges on the surface. If radiation or light hits the surface, what do you expect to happen?
It is reflected or absorbed.
Right, exactly, right. So it will be either reflected or absorbed. But if the medium is completely smooth, there are no rough edges on the medium, then all of it will be reflected, right? Complete reflection will happen. All the rays that will hit, they'll be completely reflected. However, if I have a medium that is not entirely smooth, so suppose there are some rough edges on this medium, what happens is, if the radiation strikes this type of a medium, it will, because there are some rough edges. So for example, if something is like this, light hits it and bounces back off like this. If something is like this, light would hit it over here and it would bounce off in some other direction. And it will not be completely reflected because some of the light will be absorbed in the material, right? And this light that is absorbed in the material
Less
is
than 1 minute.
rough, is in the form of heat, right? It's radiation, it's heat.
Yes.
That's
Also,
why,
the atmosphere, it is the same story for the atmosphere. The carbon dioxide absorbs,
yes,
lets some in and cannot let it out. So, global warming.
exactly.